Hello. Today, let's talk about lasers, right? Lasers are one of the four technologies that have really changed our view of the world as far as chemistry is concerned, right? It really helped us get an atomistic and molecular level understanding of chemistry. Those four technology are lasers, that we'll talk about today, but also molecular beams, which were greatly improved by the regular attainability of high vacuum. But then eventually we got to ultra high vacuum, and that really allowed us to do things as well with surface reactions, and then with molecular beams we could cross them and look at reactions one collision at a time. And then you couple all that with high-speed electronics for both detectors and of course computers that we can do computations. Those are technologies that have driven advances in physical chemistry. Now, why are lasers so interesting? There are about 5 different qualities of them that make them very interesting for doing spectroscopy and initiating reactions and studying them as well. And those are that lasers are monochromatic. Right? That is, they have a very well-defined wavelength. But not only do they have a very well-defined wavelength, they have a very well-defined central wavelength and a small bandwidth of light around that. And if we operate them in different modes, we can really get that wavelength defined very well. Now, lasers are also directional. That is, we get a laser beam, and a laser beam can be bounced off of mirrors and propagated very accurately. We know exactly where it goes. Then we can put lenses in there, and we can focus down our light to very small spot sizes as well. So we can move it around. We know exactly where the photons are. We can move them over large distances. You can even bounce a laser off a mirror on the moon and see the light coming back, which they have done to figure out how far away the moon is and how that changes over time. You can also run lasers either in a pulsed mode or CW. CW is continuous wave. And if you want to really define the wavelength and bandwidth very well, you're going to use a CW laser. But if you want time information, right, and the time progression through time resolved spectroscopy, you want pulsed operation. We can get pulses down easily into the nanosecond regime, and then the picosecond and even the femtosecond, and with some special techniques that we'll talk about later, high harmonic generation for instance, we can get to the attosecond regime as well. Combine these all together, and lasers can be extremely bright and intense. We can pack a lot of photons into a small frequency range in a small area, small volume, as well as a small time scale. So we can have very high number of photons per unit bandwidth, per unit time, per unit area, right? So we can get extremely high energy densities, that is joules per square meter. We can pack those photons into a short time in these pulses as well and get high power densities, joules per second per square meter, right? And when we pack a lot of photons into a small area in a small amount of time, we get really high electric fields. Those electric fields can be comparable to the fields that hold electrons into an atom. And we'll see the implications of that later. Then on top of it all, we can make lasers coherent. Laser radiation is intrinsically kind of coherent. That is, a good phase relationship between all of the photons. They're oscillating in phase, and they do that and have aspects of both spatial and temporal coherence. So if we look axially along the beam, they're all in phase. Or if we look transversely across the beam, they're also all in phase. So that leads to coherence, and we can use that to our advantage in spectroscopy as well. Now, there are a number of different lasers, and they were all built off of original work that it started actually in the microwave regime by Arthur Shallow and Charles Towns, right? And they got the first system with amplification of stimulated radiation to work in the microwave region. So that was actually called a maser. And then when we got to the infrared and the visible regime, that's when we really called those lasers, right? The first visible laser was the ruby laser, actually, discovered by Theodore Myman back in 1960. Then, shortly after, a year later, they had the first CW laser. It was a HENI, helium neon laser. That's a gas laser. So we see we can use different phases for lasers, right? That was used for the first laser-induced fluorescence experiment by Zer and co-workers. So that was one of its first applications to chemistry. Then, though, what really was important, because what we'd like to do is tune this wavelength to do spectroscopy, and that tunability came about with the invention of dye lasers by Mary Spaeth, Peter Sorokin, and Fritz Schaefer as well. They, working independently, discovered the dye laser, and the dye laser is tunable, so very good for spectroscopy.